Okay, so yeah, it's 12:02, so we'll get started. Welcome to Friends of ORNL meeting. I'm John Gunning, current president of Friends of ORNL. Can everybody see the FORNL announcements?
Yeah.
Okay, good. So remind people, K25 Museum, AMSE, and Manhattan Project National Historical Park are open. Last I heard, masks are required, but please visit. The Manhattan Project National Park still needs volunteers, so stop by the desk at the Children's Museum or call Christine Retchen or Daryl Long. The number's there, but the easiest way is just go visit the Children's Museum. Today's talk, Charles Forsberg will be talking about molten salt reactors, new initiatives and new directions. November 9th, it's ORNL's top 10 technology commercialization successes by Michael Paulus. And to remind folks, there is no meeting in December. So there we go. I'll see if I can get this out of there now. And we'll stop sharing now. And bring up. Okay, I'll introduce Charles Dr. Forsberg. Dr. Charles Forsberg is a principal research scientist at MIT. His current research areas include fluoride, salt-cooled high-temperature reactors, hybrid energy systems, and utility-scale 100 gigawatt heat storage systems. He's a principal investigator for building a flowing molten salt loop in the MIT reactor. He teaches the fuel cycle and energy system classes. Before joining MIT, he was a corporate fellow at FORNL. Early, he worked for Bechtel and Exxon. He's fellow of the American Nuclear Society, a fellow of the American Association of Advanced Science, and recipient of the 2005 Robert E. Wilson Award from the American Institute of Chemical Engineers for outstanding chemical engineering contributions to nuclear energy, including his work in waste management, hydrogen production, and nuclear renewable energy futures. He received the American Nuclear Society Special Award for Innovative Nuclear Reactor Design and is the director of American Nuclear Society. Dr. Forsberg earned his bachelor's degree in chemical engineering from the University of Minnesota and his doctorate in nuclear engineering from MIT. He's been awarded 12 patents and published over 300 papers. Welcome, Dr. Forsberg.
Thank you.
Now, is this still, can you see the slide? Can everybody see the slides, or do I have to re-share or something?
I'm just seeing you.
You're just seeing me. All right, we'll do this. Sorry, I had it up and clicking away.
While he's working on the slides, I'll start by an observation.
Yeah, you can start chit-chatting.
Right. I'm going to discuss or review what's going on in the world of molten salt reactors. My suspicion is if you put down everybody in the game, you'd probably have a list of 50 organizations. So I'm only going to talk about 4 of the major efforts that are underway, the 4 that I think have the most financial resources, which is important because if you're starting to talk about building a reactor, suddenly the engineering staff is measured in hundreds. It's not 3 or 4 people, and that's a different ball game when the engineering staff gets to be measured 100, 200, 300 people. And that, of course, when you add construction, it gets to be a much larger number. So I'm going to first cover some history, and then go through 4 examples, and I'll probably spend more time on the Kairos power one because they plan to have by 2026 a 35 megawatt research reactor built at K25 in Oak Ridge. And so their construction's got to start fairly soon on that, given their timelines. The Kairos is out of Alameda, California. Came out of Berkeley. It turns, as I will discuss, we've been having lots of research on salt reactors between MIT, Berkeley, and Oak Ridge. We have a slide.
There you go.
Okay, and we can go to the next slide for some history of the molten salt reactor. The reactors were originally developed for the aircraft nuclear propulsion program, that is the jet bomber. The goal is a nuclear jet bomber with unlimited range. That was before the development of accurate ice intercontinental ballistic missiles and before people had satellites to find out where cities were located in the Soviet Union. A little hard to bomb a target if you can be off by 50 miles and if you don't know where it is. And important point to observe, which I'll come back to later, which is important of the later discussion, is that the molten salt reactor was chosen because it matched jet engine requirements. We'll get back to that later of why that's important in terms of modern power cycles. There were a lot of tests, including some big ones. A small reactor was put aboard an aircraft for radiation shielding studies. And in Oak Ridge, the aircraft reactor experiment was the first molten salt reactor that was actually built. And there's a picture of the top plate on the right. Next. Now, some of you probably are much more knowledgeable on this than I am. In 1965, ORNL started up the molten salt reactor experiment. It was the second molten salt reactor, 8 megawatts. Goal was ultimately to develop a power station. Programmatically, it was electricity production and a breeder reactor that produced more fuel than it used. And the program was canceled in the early 70s with a decision to focus on sodium fast reactors. Next slide. Brief description of what I'd call the classic molten salt reactor. The fuel is dissolved in a molten fly salt versus all other reactors that are solid fuel. The breeder reactor to convert fertile thorium into uranium-233 and fission that uranium. That involved online processing of the molten salt. You obviously would have an energy source for millions of years. And one thing that's not appreciated, was very much appreciated at the time, is that these thermal spectrum molten salt reactors have very low fissile fertile startup inventories compared to other reactors. And at that time, one of the real concerns was how much fissile material was on the planet Earth. It turns out the geologists were off by about a factor of 100, some number, or maybe 1,000, but they were seriously in error. And last, whoops, we just lost the picture.
Shit, sorry. I was trying to get Jim Rome to mute, but I screwed up when I did that. Hey, Jim, mute yourself, Jim.
Last, which is often not appreciated, is that a molten salt reactor, you have the option of removing the fission products, which limits the accident source terms. And that thing keeps coming back in terms of safety. I'm not going to go into it, but it's an important future option. Could I have the next slide? And key item, all salt reactors operate at high temperatures. That's important in later discussions. We have a list of various salt coolants that people have proposed, plus water. The first column is the melting point, and the observation here is it's between 450 and 500 degrees. Boiling points are right through the stratosphere, and the implication is that the operating ranges of these reactors will be somewhere between 550 and 700 C. So these are intrinsically high temperature machines. This is not the place to go if you like low temperatures. And let's go to the next slide. Today I'm going to discuss molten salt reactors, and the key message is they're back. People are spending lots of money on them. And there are two classes. The first are the clean fluoride salt cooled reactors of various kinds. And I'm going to discuss the Kairos Power fluoride salt cooled reactor that's proposed for Oak Ridge. I'm also going to discuss the Commonwealth Fusion ARC concepts, which is a fusion concept that uses flibe salt coolant. The second class on the right is where the more classical machines, fuel dissolved, either a fluoride salt or a chloride salt, many variants of both. I'm going to describe one of each category. Classical molten salt reactor that people are currently working on. I should also mention the Europeans have been working on a molten fluoride salt fast reactor. There are also chloride molten salt reactors that's longer term, and I'll discuss one option a little later on the talk. Well, could I have the next slide? Why the renewed interest in salt reactors? The first one is economics. High temperature heat to the customer. One of the interesting things about the molten salt reactor experiment is when it was built, it did not couple well to existing steam plants. That's because it ran at such a high temperature compared to the steam plants of the day. That's no longer a challenge. Steam plant temperatures have gone up. And second, in a low carbon world, you need industrial heat. And so this high temperature characteristic is what the customer buys the reactor for. Second, there are safety advantages, but that depends on the particular machine and their fuel cycles, but we now have a lot of different fuel cycles. Could I have the next slide? The economic basis for salt reactors is higher temperature delivered heat. And what I show on the far left are the four traditional coolants: water, sodium, helium, and salt. And water has inlet temperatures around 270, exit around 290, which means the average delivered heat is 280 C. Sodium reactors go between 450 and 550 C. Average delivered temperature about 500 C. Now, helium-cooled reactors, high-temperature reactors, we keep thinking of them as high temperature. However, they have low inlet temperatures, about 350, and typically exit temperatures of 750. So the average delivered temperature is around 550 C. In salt reactors, they're in the 600 to 700 range, which means that the temperature of the delivered heat, what the customer pays for and what the customer actually wants, is about 650 C. And I emphasize that from a customer perspective. Can I have the next slide? Now, high temperature heat enables advanced fuel cycles. This slide could be an hour talk by itself, so I'm not going to say very much about this, except starting with the observation is that molten salt reactors are designed to couple to a jet engine. And the most popular power plant today is the combined cycle gas turbine. And that's a consequence of 70 years of advances in gas turbine technology. And because salt reactors were designed for these things, they actually couple pretty well with them. There's a lot of work on something called a nuclear air Brayton cycle with heat storage. You operate the reactor at base load, but it is variable output to the grid. And what I mean by variable output is you have the reactor providing heat in the light blue to the multiple turbines. But after the turbine 2, you can operate in base load, or you can take the temperature from let's say 650, 700 C, and inject natural gas or hydrogen in to boost the temperature for the last turbine in the gas turbine cycle up to about 1400 Celsius if you want, blazingly warm. And when you do that, that booster stage, that peak power capability results in a system where the incremental gas or hydrogen heat to electricity efficiency is over 70%. It's a thermodynamic topping cycle. So there are lots of things you can do if you can couple your reactor efficiently to a gas turbine, which fortunately was the design criteria for molten salt reactors. And there's an open source article if you want to go into the gory details of what that involves. Could we have the next slide? Now, the next set of few graphs are going to cover clean salt systems. So these are clean salts. There's no fissile material in the salt. I'm going to discuss two, what Kairos is up to, and Commonwealth Fusion ARC system. Next slide. Chloride, salt-cooled, high-temperature reactor, clean salt, solid fuel. This is being developed by Kairos Power. It's a 35 megawatt test reactor. It's the first one they plan to build, which should be operational by 2026 in Oak Ridge. Kairos has about 200 full-time people plus an awful lot of part-time people and consultants and contractors. So it's a substantial effort to get that reactor built on time. Next slide. The FHR is a pebble bed FHR with flied salt cooling. You have the high temperature fuel and the liquid salt coolant. Can I have the next slide? Okay, I'm gonna make there's a newer version of this slide deck that I sent you, but I'll just mention what's in the newer version of the slide deck in passing. The fluoride salt cooled reactor came out of Oak Ridge National Laboratory, and that shouldn't be too terribly surprising because it combines liquid salt with HTGR fuel, and Oak Ridge had major programs in both areas. So there were lots of people that became very familiar with that particular reactor concept. Now, it turns out in about 2002, there was a Gen 4 meeting, and myself and Per Peterson of Berkeley and Paul Picard of Sandia were on the miscellaneous reactors subcommittee. And we went out to lunch and were not very impressed by the odds and ends that people had proposed. And out of that lunch came the FHR, which combined high temperature reactor fuel with molten salt. And that had a lot of advantages. The HTGR fuel goes to very high temperatures. When you go from a gaseous coolant to a solid gaseous coolant to a liquid coolant, your cooling capability goes up dramatically. It's a tremendous difference. And so you can get the power density up by a factor of 10. You also have a whole bunch of safety advantages. It's a low pressure system. And beyond that, if you have any leaky fuel, it dissolves very nicely into the liquid salt. So it's not going anywhere. This shows a picture of the Kairos Power design, the reactor nuclear island, and the safety case. The first one is this uniquely large temperature margins to fuel failure temperatures. The second one is the salt, which has a boiling point over 1400 C. Now, the combinations of those two features is you can't melt this reactor down and you can't have an accident in the core. Now, you could run the temperature high enough to melt the pressure vessel or the vessel, but you can't start an accident in the core, which is sort of unusual because everybody else's accidents start in the core. It's a low pressure system and it has a very effective passive decay heat system. The implications of this is actually lower capital cost because you reduce the requirements for high cost nuclear components in structures throughout the plant design compared to an existing light water reactor. Could I have the next slide? This is sort of a summary of what's going on. Kairos in Alameda is in a big aircraft hangar. It turns out Alameda used to be the Alameda Air Station in San Francisco Bay, and they leased on a long-term lease one of the big aircraft hangars, which is a perfect lab space. And they have the rapid prototype lab in that lab location. They also have the salt lab with all the flied salt chemistry and materials testing. They have a second facility coming online in Albuquerque. This is the engineering test unit and training facility. This is where the big equipment goes. As I will describe a little bit later, like on the Hermes reactor, they will build a non-radioactive version of the Hermes reactor in Albuquerque and run it, shake it down, and that will be used for the design of the Hermes reactor. They have an engineering test unit, which is going to be the same size as Hermes, and they've filed a preliminary safety report in September. And of course, the Hermes reactor will get built in Oak Ridge and is supposed to be operational by 2026. Could I have the next slide? The Kairos power design. This shows the engineering test unit, and it shows the sequence of activities. They're doing a lot of laboratory tests in Alameda. Then they move to Albuquerque, where they have the engineering test unit. That's the full scale, same scale as the Hermes test reactor, where they have the flibe salt at temperature and shake out everything from control rods to pumps to instrumentation. Then they move to Oak Ridge, where you have where Hermes will be built. It'll be about 35 megawatts. And that's about a 20-foot high vessel, to give you some perspective. And then they have after that, they'll go back and build the full-scale non-radioactive variant of the FHR in Albuquerque, and that leads to the commercial plant with a power output of 140 megawatts per unit. One of the things you'll note about this is, as a salt-cooled reactor with solid fuel, is the vessels are actually pretty small. And that's partially because liquid salts are a great heat transfer fluid. And if you have a HTGR fuel, you can run a lot of delta temperature drop across the fuel to heat the salt. So a lot of things come together for a fairly small reactor. Could I have the next slide? Well, I'm now going to shift gears to the fusion salt systems. And if I could have the next slide, describe what's going on. There's been a breakthrough in magnetic fusion with Repco superconducting magnets. Turns out that the size of a fusion system varies 1/4 power of the magnetic field, not fuels. And there was a manufacturing breakthrough of Repco supermagnets about a decade ago that enabled doubling the magnetic field. People had wonderful superconductors. There was only one small problem. They could fabricate them at the milligram scale. And that doesn't work very well if the quantities of superconductor you need are measured in tons. But about a decade ago, somebody finally in the manufacturing space figured out how to do that. Why is that important? It reduces the fusion machine size by a factor of 16. And what that implies is that the power density in the fusion blanket increases by an order of magnitude. It makes it very difficult to cool solid blankets. Got a big problem there. The other thing is those very high magnetic fields create very large incentives to have a low electrical conductivity to avoid coolant-magnet interactions. And the solution is a liquid flibe blanket. Now, these blankets have been looked at before, but they have not been high on the priority list. But with these much higher powered fusion machines, suddenly salt blankets look like it becomes the preferred option. Could I have the next slide? MIT did the initial analysis and the initial studies of this kind of system. And MIT and Commonwealth Fusion, a spin-out company from MIT, built the first large-scale magnet test. Because to make this machine work, the whole question is, can you build a 20 Tesla, a really big, high-powered magnet? And that was tested last month. So I think you can safely say that all future fusion machines are going to be using that magnet technology. And with it comes very high power densities in the blanket and big incentives to develop flibe salt blankets for fusion. So the fusion game is driving in the same direction of developing flibe salt. Could I have the next slide? This is the arc fusion concept on the left. That'd be about 500 megawatts. You have the plasma fusion in the middle, and then you have the blanket. And the blanket gets all of these 14 MeV neutrons, and all of the heat is generated in the blanket for the power cycle. And so what the salt does is absorbs that heat and sends the hot salt to the power cycle. The other thing is the neutrons, after they slow down, interact with lithium and beryllium to generate tritium, and that's the fuel. Now, one important observation about this is in a fusion machine, you use lithium-6 to maximize tritium production, which means the tritium production rate in this machine is about 1,000 times higher than it is in the Kairos FHR. So these guys have what you call a serious tritium challenge in containing the tritium. That was an issue for the molten salt reactor, but for these guys, when it's 1,000 times larger, there's going to be a lot of work on tritium control systems. Next slide. Why fly salt? No power limit on the power density. Second, you can maximize tritium production with lithium-6. A whole bunch of nuclear reactions generate tritium. There's a beryllium N2N reaction that works quite nicely with these high energy neutrons. And there's lithium that yields a neutron plus tritium. Last, which is most people don't appreciate, is of all the salts, FLiBe actually has the best heat transfer properties. There are a lot of other salts, fluoride salts, but turns out that if you do the heat transfer experiments, FLiBe is the salt you want to use if you got a serious heat transfer problem. With that, let's turn to the next slide. The next step is SPARC, a plasma break-even experiment where the plasma gain hopefully will be greater than 2. That is total energy out is twice energy input. 50 to 100 megawatts for short durations. It's a physics testing machine. It's not an engineered machine for power production. And if they're successful, it'll be the first break-even fusion experiment in the world. ITER's due to go online another decade beyond this, so that's not the competition. And the goal is to actually build this thing in a decade. And if you look at the size of the person there, it's a relatively small machine because of those big magnets. With that, let's turn to the next subject. And now I'm going to discuss uranium plutonium fuel dissolved in salts. And I'm going to use 2 examples. I should mention, by the way, in terms of funding, my guess is that the previous 2 fission examples probably have, fission and fusion examples have the most funding. That's nobody's publishing how much money they're spending. But if you look at the number of people at the size of the laboratories currently, I think the FHR and the arc fusion system have the highest burn rate in terms of money, because I know that the Alameda site's got 200 people full time on it, and then you've got Albuquerque thrown in and a few others, so they're burning money at a good clip. These other 2 examples are also burning money, not quite at the same rate, I don't think, though. But the next one on the next slide, they're working hard to catch up, and they will catch up. That is the molten chloride fast reactor. That's being developed by TerraPower, a Bill Gates company. It's uranium, plutonium dissolved in molten chloride salts. This is a concept that, well, chloride salts have been around a long time. As I will discuss, this particular concept is less than a decade old. Could I have the next slide? 2 classes of molten chloride fast reactors are being developed. The first one is the molten chloride fast reactor, with the reactor being a wide space in the loop. The big player is TerraPower with Southern, which is a utility with a plutonium uranium fuel cycle. The other company is Elysium with a plutonium uranium fuel cycle. The Chinese at Sinap are also looking at this with the uranium-233 thorium fuel cycle. The second version is a molten chloride fuel salt in tubes with clean fluoride salt coolant being developed by Moltex in Great Britain. They have a clean fluoride salt loop, which makes it easier on the primary loop. And it's sort of similar to a sodium fast reactor, except it's really simple to process the fuel because you have liquid chloride salt in the tubes. As you cut off the tubes, you just pour the the chloride salt out. So it's really fast, simple reprocessing if you choose to go that route. Next. Now, TerraPower is a little bit different as a nuclear company. They defined goals, and then that led them to choose the reactors they wanted. They wanted the usual things: engineered safety, minimize energy cost, offer new options for nuclear waste, maximize proliferation resistance, which is a very big issue in terms of their priority set, and provide global scale energy. And what the molten chloride fast reactor they've developed is a once through fuel cycle. After the first course starts, after the first course startup, burns either natural or depleted uranium. So you start it up, and after that you put in a little depleted uranium and take some of the fuel out. This particular kind of machine can get 25% of the uranium burnt up. And that's very close to what a breeder reactor, traditional breeder reactor, can do with full recycle. That's versus 1% with a light water reactor. Now, it was not recognized until a decade ago that such a molten chloride fast reactor with a once through fuel cycle was actually possible. And it turns out there were some question marks on the chlorine cross sections. And of course, who has an interest in chlorine cross sections with a couple of MeV, in the fission range? Nobody was looking at it, so nobody had an interest in it. In addition, it turns out to make this machine work, you have to use chlorine 37, the low cross section. Chlorine 35 is a sky-high cross section, which will shut down anything. So it's not too surprising. Measuring certain cross sections was low on everybody's priority list. Then somebody measured it and they said, whoops, a little bit off on the estimates. And then everybody was off to the races. So it's a new concept based on some new knowledge in the last decade. Could I have the next slide? TerraPower once through breed and burn. This machine has a really hard neutron spectrum, very high breeding ratio. Convert fertile uranium-238 to fissionable plutonium-239 and fission the plutonium. Again, start up the first reactor with enriched uranium chloride, uranium, sodium, potassium chloride mixture. Add natural uranium and throw away some of the fuel salt with fission products and actinides, a deep borehole or equivalent disposal. And as what I said, the really interesting thing is you can burn 25% of the uranium fed into the machine, assuming you get the machine to work. Next slide. Status, they're partners with Southern Company. What they plan to do is a molten chloride reactor experiment to be built within 5 years, located at Idaho National Laboratory in their Lotus facility, formerly known as the Zipper facility. It's a 200 kilowatt physics experiment to make sure the reactor kinetics are understood in the system. But the flow rates are 15 to 50 kilograms a second. And of course, it's primarily demonstrate the concept in the safety case. And it'll be a very simplified system. They'll use high enriched uranium and sodium chloride, which will be able to answer the reactor physics experiments. The physics analysis all indicates the machine should be stable in terms of reactivity and kinetics and so forth. But this machine is so far away from everybody else's design space that the answer is, you better go out and try this out just to make sure we haven't messed up somewhere in the calculational space. Next slide. The molten salt reactor. I'm going to discuss Terrestrial, this Canadian company, has a US subsidiary. It's a traditional molten salt reactor with fuel dissolved in salt with a simplified version of that machine. Could I have the next slide? Terrestrial energy, molten salt with simplified fuel cycle, thermal neutron spectrum, graphite moderated, enriched uranium fuel salt, no liquid processing at the reactor site. It'd be a burner reactor for the first generation, but a pathway to a breeder reactor. Next slide. This integrated molten salt reactor, the goal is about 195 megawatts E. A reactor vessel with graphite core that is replaceable every 7 years. Essentially, the factory delivers the module. You run it for 7 years, they send you a replacement module. You let the module that you took out sit for a while, and then you send it back to the factory for refurbishment. And the goal is to simplify plant maintenance. All of the fuel salt remains in the module. And the module contains the fuel salt, the graphite, and the intermediate heat exchangers. The off-gas system is separate from the module, and the goal is to absolutely minimize reactor site operations and let all of the complicated operations, such as replacing the graphite, be done at the factory. And so, the design feature is that the graphite core and main heat exchangers, only clean salt leaves the module. So it's a package. It's a package system where you send it back to the factory when you're done. Now you can move some of the salt from one unit, modular unit, to the next unit at the site, but the idea is to really minimize this from the utility perspective and let the fuel cycle guys deal with everything else. Can I have the next slide? This happens to be the flow sheet of their system. Three loops: a primary loop with fuel salt, a secondary salt loop, and then a nitrate salt loop, which is the tertiary loop. And the FHR also has a nitrate salt loop, and so does the different salts proposed for the TerraPower one. And the thinking here is that with a nitrate salt, you can put in heat storage for variable output with baseload input of heat. Most of you may not be aware of it, but all of the big concentrated solar plants use nitrate salt as their heat transfer loop, and they store gigawatt hours of salt in hot and cold tanks. And if you have a nitrate salt system in the intermediate loop somewhere, you can put in gigawatt storage to handle daily to weekly cycles of heat of variable energy demand while the reactor operates at base load. Essentially replace the gas turbine, the role of the gas turbine in the power system. And could I have, I think, which is the last slide? Well, serious money is going into salt systems: Kairos, TerraPower, Commonwealth Fusion. The first reactor that's supposed to go up online will be the test reactor at Kairos in Oak Ridge. The TerraPower is probably going to be a little bit later at the critical facility, although it could be pretty close. It's because it's a much smaller experiment. But they've only begun to work on that and don't have the manpower up. Toward the end of the decade, Commonwealth Fusion proposes to have their break-even experiment up and running. And all of these efforts are burning what I'd call some fairly serious amounts of money. And they measure their manpower in hundreds of people. So it's you're way beyond laboratory scale operation. You're doing a lot of stuff at the pilot plant scale. A lot of hardware development, technology overlap, and very different goals by different developers. Each of these developers has a different set of goals and a different set of timelines. So with that, I'll stop and open the desk. I'll open the floor to any questions.
Okay, let me minimize this so we can see people and
Hello.
and then I had put while people are you could put your we got 8 questions in chat. Here we go. All right. John getting where could we get a link? Okay, the link will be on the FORNL website. It's my okay.
May want to also put up the
Your comments were related to Zoom, so that's fine. Let me ask the first stupid question. Since your MIT fusion focused thing, it seems to have a quantum break in the magnetic fields. I guess the obvious question is, how does this affect what ITER's doing? I mean, ITER is not, I don't know.
There's a $20 billion question to which nobody knows the answer.
Okay, so it's a reasonable question, I guess, right?
It's a reasonable question, and I'm sure it's a really sensitive subject. What happened on ITER is, well, they first initially had some pretty bad management. They fixed that problem, but you have a very long timeline. And then these guys came up with this superconducting tape. And there's a bunch of people who manufacture superconducting tape. And what they wanted to do is for hospital magnetic imaging machines is they wanted a lighter weight machine for hospital tests where you didn't have to put it in the basement, because the existing machines are so heavy, if you put them on the second floor, they go through the floor. So their goal was a better imaging machine to sell the superconducting tape to GE and Siemens that make medical devices. And then the MIT fusion guy said, now, wait a minute, you just solved the problem. But the funny thing, it wasn't a science breakthrough. It was a guy there who figured out how to make this stuff. It was a manufacturing breakthrough.
Okay, there's somebody says, does Kairos use 20% enriched uranium?
19.5.
Sorry?
19.5%.
Oh, essentially. Okay.
Yes, yes.
All right.
And
All right.
that's done for a couple of reasons. Now they'll have a burnup in excess of they'll have a burnup around 200,000 megawatt days per ton, and the game is to minimize the amount of fuel fabrication and minimize the amount of spent fuel. They'll have about twice as much spent fuel as a light water reactor in volume, but it's pretty hot burnup. It's 200,000 megawatt days per ton. That's a pebble bed reactor, and what is interesting about that is the time it goes through the reactor multiple times, but it'll go in and out of the reactor to fully burnt up at 200,000 megawatt days per ton in 18 months. Once you get one of these machines started up, you want to test a different kind of fuel, you get results fast.
Next one, it says, are there proliferation risks that are unique to molten salt reactors?
That depends. If it's solid fuel, there's no difference compared to other solid fuels. Actually, it may be better than other solid fuels because this graphite matrix fuel is harder to reprocess than other fuels, and that extraordinary burnup means it's not going to be a very nice grade of plutonium in it. The molten salt reactor, the issue is there may be concerns, and there's a lot of debate because you want to do online monitoring of your fissile inventory. There's a lot of work on that, but I haven't been following the gory details very much.
Okay, it says, will the lithium-7, what will be the lithium-7 enrichment for Kairos?
Oh, it's I forgot. I think it's 99.5, but I'm not sure. I forgot what the number is.
Okay, so we'll
and they're setting up a lithium-7 production line. This lithium enrichment line.
Okay, why did Kairos drop NaCC in favor of thermal storage? First, explain what NaCC is, please.
That's the gas turbine option. For the first reactor, the game is minimize technical risk, buy everything off the shelf if it isn't required to be new. And so the first generation will be a steam cycle. They can use the nitrate salt storage for meeting customer demand. The nitrate salt also acts as a backup tritium capture if they have any leakage of tritium from the reactor. By the way, they're not the only ones pushing or planning to use nitrate salt intermediate loops. GE and TerraPower plan to build a sodium-cooled reactor, the Natrium reactor in Wyoming, sometime in the next decade. And that will have an intermediate salt loop for heat storage to enable baseload reactor operation with variable power to the grid. So everybody's putting in the classic, everybody who's building a high temperature reactor is putting in the classic solar power tower heat storage system because of the nature of the electrical markets, where the price of electricity goes up and down like a yo-yo. This is all market driven.
Okay, Trent asked, it says, South Africa supposedly were not able to manufacture pebble bed successfully. Will Kairos make their own fuel or buy from someone else?
My understanding, they're in the middle of that debate. They have option A and option B. What is important to note is the Department of Energy had something called the NGNP program, Next Generation Nuclear Reactor Program, which was to build an HTGR. And that program got killed ultimately by cheap gas, but they continued the fuel development program, which was very, very successful. When you build this coated particle fuel, people had variable experience making the stuff. And the Germans learned how to make it, but it was what I'd call a black recipe. You know, if you do this, you do that, we're not quite sure why you do it that way, you'll get the right fuel. What the NGNP program did in their fuel development program, including testing in both HIFER and ATR, is that they finally understood what they were making. You know, if we do this, this will happen. They understood what changing the parameters in fabrication space meant in terms of performance. So the coated particle fuel has gone from an art form, which it really was, into something you can make, and you have a lot of ability to vary the design.
Yeah. Okay, says are the MSR components made of alloys that can resist chemical corrosion and radiation damage from salts containing nuclear fuel?
We think so. Now, I need to make a very important distinction about this. If you have clean salt, life is a lot easier. In the molten salt reactor experiment, the secondary loop had clean salt, and they didn't see any corrosion. The primary loop, they saw corrosion because of tellurium fission products. And so people think they have that problem solved, but I'm not sure if, you know, they may need more data on it. But for clean salts, people have a very high comfort level that the corrosion problem is easily fixed. It is fixed.
Okay, the Senate ask is says a specific power for Kairos, TRISO, probably much higher than those in a high temperature gas reactor where most of testing was done.
Yes, but the NGNP program covered a lot of different power densities. The other thing about the Kairos HTGR fuel is their spheres are actually going to be about the size of ping pong balls. And the fuel is on the outer part of the ball. There's a core that's actually graphite, so they run at a pretty low temperature compared to some of the HTGRs. And of course, they have liquid salt cooling, which is a whole lot better than helium.
And it says, are thorium molten salt reactors, say LFTR, the breeder, more prone to proliferation concerns?
You mean compared to, it depends what you compare it to. When you get into proliferation concerns, if you're comparing molten salt reactors, you're in a very complicated space. That's probably worth a separate talk all by itself. You know, the big thing is people haven't done a lot of thinking about the problem. That's the real difference. People have been thinking about solid fuel reactors where you go count, and in a molten salt reactor, you don't count items. You have to keep track of a liquid inventory.
Fuel qualification program test. I guess that's a statement rather than a question. Fuel qualification programs will test high power densities for commercial use. I guess use that as a question, I guess.
Well, first, some high power density tests were done at Idaho and ATR as part of the NGNP program. So there is a significant amount of data out there. The second one, which is sort of interesting, is, you know, the burnup times in this reactor are 18 months. You can get a lot of data back real fast on higher burnup in a FHR. You can get it back faster than any other reactor. So you end up with a very short fuel development cycle compared to anybody else.
Trent asked, will a Kairos reactor have a containment building?
It'll have a containment, but I haven't read the PSAR, which I'm sure if I printed it out, it's got to be at least 2 feet, maybe 3 feet, unless they've dramatically changed. But I have not printed out the PSAR, or I haven't even looked at it. So, of course, they only sent it into the NRC last couple of weeks ago.
Okay. The best nuclear material proliferation is a fusion reactor, but put U-238 in the blanket and make all the plutonium you need from 14 MeV neutrons.
That's absolutely right. Fusion is going to have safeguards associated with it, and the safeguards, you can guarantee that you build a fusion machine. The safeguards guys are going to have all sorts of detectors to make sure they don't spot the gamma rays from any fissile material in the machine, because otherwise, you're right. It's the best neutron source on the planet Earth, short of setting off an H-bomb, which is even a better neutron source. But yep,
Well,
yeah, they're going to be detector. Every fusion machine, if they actually make it work, every fusion machine is going to have all sorts of scintillation counters looking for fissile materials to make sure that isn't done.
And what is the longevity of the salts, given that they will be exposed, and then how are they disposed of?
The salt essentially lasts forever. I mean, you slowly break, you just turn the lithium into tritium and the beryllium, but the salt lasts forever. What doesn't last forever is the first wall. And I didn't go into the details, but the MIT Commonwealth ARC machine has a very neat strategy for that. It turns out that they have what they call demountable magnets, which means the top set of magnets can be physically separated from the bottom set of magnets in a very clean way, quickly, like in a couple of days. So their strategy is they will literally replace that inner wall structure that separates the plasma from the salt tank every couple of years. So instead of they going a refueling outage to replace the fuel, they'll have an outage to replace the blanket structure that sees this massive neutron flux.
Keep coming. So would the Chinese WUWI, which I guess is thermal TMSR, thermal molten salt reactor, have a large impact on TMSR worldwide? Basically, what's your forecast on the impact of the Chinese?
Well, the prediction is they're going to start it up this year, but I haven't seen any pictures yet. And that'll be a 2 megawatt machine, and it's designed as a test bed to test things like off-gas systems and salt cleanup systems. Obviously, if the Chinese get going, the Chinese know how to build stuff in a hurry. They've demonstrated that at a fairly consistent rate. The current plans are on regular light water reactors is they're going to commission 6 or 7 of them a year, and then they're going to get serious. So if they're successful in developing a molten salt reactor, yes, that will clearly have an impact having a classical molten salt reactor. And they got big plans, but the emphasis on that 2 megawatt machine is essentially we have a way to test off-gas systems, a way to test salt processing systems using real salt that's been really run through a real molten salt reactor. Nobody has any doubts that the physics works. Nobody has any doubts that the graphite works. What you worry about is the practical, economic, reliable systems for off-gas and salt cleanup. And what that machine will do is it'll provide you a 24/7 source of hot off-gas and a 24/7 source of liquid salt to do your processing experiments on.
Dave Fields points out there are a number of basic research areas that have to be pursued to avoid surprises, such as salt-induced metal corrosion with mixed impurities, isotopic cross-section, thermal recycling effects on components, magnetic material degradation from neutrons. He asks, is this basic research being done in parallel with the technological experiments?
Well, thanks to COVID, I haven't been to Shanghai recently. This is being done by Synap in Shanghai. And the last time I was there, they had about 500 people working away on it. And they had everything from small labs to big labs. So everything from laboratory experiments to pilot scale.
I think this wasn't specific to the Chinese. This is just MSRs in general and all of the.
The molten, the classical molten salt reactor, fuel dissolved in the salt, they're the biggest effort in town. On the clean salt system, Kairos is the biggest effort in town by I think a reasonably large margin.
And finally, right now, it says, how useful would a smaller size nuclear be on the moon or Mars? NASA seems to be, we think seems to be interested.
I'm not the expert to, I have my own opinions, but I would not claim to be knowledgeable on, or you probably need to get a speaker that specializes in that.
Okay.
You know, I read the same literature everybody else does.
So I want to first thank you and congratulate you on your talk. I thought it was very well done. I also thought we had a very excellent question and answers
I have a question.
session, and this chat works well and lets people formalize their thoughts, and then we can go through them. Let me just finally, since we got through them, if anybody else has a question, raise your hand and I'll try to call you out. Gary.
The chloride salts had a major problem of isotopic separation and material compatibility. What happened to that?
Well, the chlorine, you have to do the chlorine 35-37 separation. And actually, I wrote a short paper on it. Turns out those were the first two isotopes were separated. And that's a fairly easy separation to do. Remember, they don't need 99.99% chlorine 37. They probably need 95% chlorine 37. And my guess, I don't know, but my guess is it's either going to be some permeation membrane, or it may be just distilling hydrogen chloride in a big oversized distillation column, which will also separate the isotopes. So there's lots of option space, but I don't know. TerraPower's got some people working on the problem. They got a pilot plant somewhere, but they haven't released any information on who's doing it and where the work is.
Materials compatibility.
Well, they have several dozen salt loops running at any one time to work on material compatibility. They think they'll get the problem solved, but they're running somewhere between 50 and 100 loops, very small corrosion loops. They got a lab that's just full of corrosion loops.
Do they have anything in the offing that shows promise?
Well, let's put it this way. If you're deciding to go build an experiment at Idaho with HEU and sodium chloride, you obviously think you're at least a fair way along on getting a compatible materials of construction, or you wouldn't start pouring that kind of money in. I mean, these guys have a high burn rate. You don't do high burn rates unless you have some reasonable confidence. But of course, they're pretty proprietary on the materials of construction.
One of the major advantages of molten salt fuel is that it has online preparation and processing. Why give up on that?
I think everybody thinks it's easier in the near term to get clean salt. You know, if you get a clean salt, if Kairos is successful, you're halfway home to a molten salt reactor, because it's not only the salt handling experience, but it's also materials of construction, instrumentation, pumps, power systems, heat exchangers. There is an awful lot of stuff that is identical whether you're doing a molten salt reactor with fuel in the salt or clean salt. And if you're thinking commercially, the near-term option, and certainly a much lower technical risk option, is the FHR. But everybody's got pathways that go out in time.
Let me ask a final question. Since you went to the molten salt workshop at Oak Ridge last week, is there anything significant from that you'd like to share with us?
Well, I noticed Dave Holcomb just showed up. He's probably the right one to answer, since he was the MC or the chairman of the panel. Well, I think the main thing, two things come through. The the first is there's an awful lot of work going on in the United States across the board. And then you've got these 4 efforts that I've described that are, are seriously into the engineering of these systems. So that's something you wouldn't have seen 2-3 years ago. You can now, you're talking about sites, preliminary safety analyses where you measure the paperwork in feet, except that I'm sure they send it electronically as PDFs rather than back. Well, I'm not sure. Maybe they do back up the truck to the NRC and take out the pallets with multiple copies. It's a good question. You have to deliver 20 copies on pallets of your PS. I apologize for my laughter about this, but the difference is we're moving into serious hardware, and that's been a long time since people are talking about facilities going critical. And cold laboratory tests are in 4-story, 5-story high bays because they don't fit into the smaller stuff.
Well, let me conclude. I think many people had a chance to answer or ask some very interesting questions, and I think you very capably answered them in a succinct fashion and kept going, which is impressive, which not found in all speakers. And I want to personally thank you on behalf of myself and Friends of ORNL for taking your time to provide your expertise to us. So,
Yeah, thank you, Charles. Good to see you.
Thank you again, Charles.
A lot of familiar faces.
Yeah, take care.
And
Good seeing you.
just to let everybody know, we at least
Yeah. Yeah. Thanks again, Charles. Good presentation.
Yeah, we had folks, we had like 61, at least 61 participants on this. So we're doing quite well in our Zoom meeting. So.
And Kent's with me, so we count double.
Oh, yeah. All right. Sorry. 62. All right.
Take care, Charles.
Yep. Thank you.
Good luck to you. Good seeing you.
Thank you very much.
Thank you.
Bye-bye.
Everybody enjoyed it. Very good.